Uh, we are pleased to introduce Mr. Milind Trivedi, an accomplished embedded systems and power electronic professional with over 18 years of rich experience spanning academia, industry, and entrepreneurship. Mr. Trivedi is the founder of Embed Logics, where he works on embedded software and hardware design, EV charging solutions, automation, IoT, and professional skill development. Prior to this, he held key technical and leadership roles at Quest Global and Bombardier Transportation, Alstom, contributing to critical rail and battery operated train BEMU projects in the compliance with international safety standards. He has also served as an assistant professor for more than 13 years, uh, teaching core subjects like microcontroller, power electronics, motor drives, embedded programming, etc., uh, making him uniquely positioned to bridge theory with real world industrial practices. Mr. Trivedi holds an MTech in Power Electronics and Industrial and Electrical Drives from SVNIT Surat, where he was awarded the gold medal for academic excellence. His expertise includes embedded C, C++, ARM Cortex controllers, motor control, BLDC, PMSM, field-oriented control, CAN-based communication, and rail-certified embedded software development. We are confident that his insights and practical experience will add immense value to this faculty development program. So please join me warmly welcoming Mr. Milind Trivedi. Sir, you may start your talk.
Okay, so good evening, everyone, and thank you, Professor Chirag, for inviting me for this session. And a big congratulations to SNPIT College for organizing such an FTP with this AI domain. So, as you all know, embedded systems are everywhere, like powering our cars or medical devices, smart homes, automations, or like countless everyday products. So the thing is, even if the complexity is keep growing every day, there is also a growing need of faster time to market, higher reliability, tight power, size constraint, memory constraints, etc., etc. So on the other side, we are witnessing a remarkable rise in artificial intelligence, tools that can learn, that can reasoning, us that can generate code, that can detect patterns and automate things for us or automate the complex tasks. So the important thing is how AI could help become a practical co-engineer in firmware development. So how can we accelerate the things? How can we accelerate the development without compromising on reliability and performance? So today, my topic would be basically to how to accelerate the firmware development in embedded systems using AI. So let me share my screen first. Is it visible?
Yes.
Yeah, okay. So we are talking about how AI can become a practical co-engineer in a firmware development. And preferably, we are talking about how we can accelerate the firmware development in embedded systems. Not as a replacement for engineers, but as a powerful assistant. So we will look at where AI fits into the firmware lifecycle, real world use cases and practical benefits, and the challenges that will come alongside adopting the AI. And today, because you are already aware about the AI and already attended so many sessions on this same domain, I plan to talk bare minimum theory on this topic, but my plan is to show you a practical demo how AI can accelerate your firmware development, what are the challenges, and how we can solve those. So, do you have any question? You can, I think, you cannot directly unmute yourself, maybe. But if you want to connect with me or at any point of time today at later stage, you are welcome to do it. So basically, in my company, I'm majorly focusing on this hardware and firmware development, especially in microcontroller, microprocessor domain. My majority of work is based on the 32-bit microcontrollers, and of course the hardware design, software design, PLC, SCADA, automation, everything is there. So till this date, I mean, before, if you talk about before, like a year or maybe 8, 9 months, I was not using AI at all. So I was like hard coding everything, and everything was manual. The design, development, writing, debugging, testing, everything was manual. But now I also start using AI at such a particular specific case. I'm not relying completely on AI, but yes, AI can certainly help me to have the accelerated development. So uh, let's directly come to the point. Like, what is an AI model? If you talk about that, AI model is nothing but a mathematical model trained on large data sets. So it's a lot of data sets available on the internet, and that model is fed with those large data sets. The AI can learn patterns from text, code, data, and it can assist humans in reasoning and problem solving. And if we just talk about the evolution of AI, it's like the initial AI was rule-based systems where if-else logic was there. So it's a strict rule-based pattern. There was no reasoning, intelligence, no learning patterns, etc. Then there was a classic machine learning approach, deep learning approach, and nowadays what we are currently seeing is a large language models called LLMs. So the LLMs is nothing but it's the model is trained on massive text and code database, lots of articles, lots of papers, lots of data sheets, lots of application notes, user code, GitHub, GitLab libraries, and everything. So these models will have a lot of literature trained on that. It understands language, logic, programming. It can reason, explain, generate code. For example, ChatGPT, Claude, or Gemini, whatever you say. These all are nowadays based on large language models. So question is why AI is useful for the firmware. So it's basically firmware is what? It's just a text. I mean, it's a coding. So you type something, you need a logic to type something, and then you have some constraint. Like if this happens, then only this thing should be done. So the text, logic, constraints, and everything is under the control of firmware. So firmware can do each and everything. It can type something, it can perform a logical operations, or it can provide the results within some constraints. It requires reasoning and pattern recognition. So you always know that whenever you write firmware, there is also a pattern, there is also reasoning. Why you write this code or why you have chosen this particular thing. That's something which we require, and that AI can do very easily. And AI understands the protocols, drivers, and architectures. That's a very important thing. Like all the protocols nowadays, what embedded systems currently uses, like Ethernet, SPI, Modbus, UART, whatever you say, all the drivers, all the architectures, all the drivers, protocols, architectures are known to the AI. So that's why our focus should be on developing or designing the overall system rather than writing a specific protocol. How AI can help for firmware development. This is very important. How this can help. So first of all, you can say it helps the code generation. So when you elaborate the code generation, it's basically, you can say a peripheral initialization, like all the peripherals, it can initialize for various MCUs. It can write the interrupt service routine called ISR. It can write your overall state machines of the system. It can suggest you what should be the state machine based on your particular application or requirements, and also it can generate a code for the error handling. Then it can have data sheets and debugging, so it can explain the data sheets, registers, everything it can be done. Architecture and RTOS. The most important thing is if you are in a development, if you want to decide between whether you go with the bare metal environment or you go with the RTOS environment, that decision has to be taken, and that decision has to be taken by you or AI. Like for example, it should be taken by you, but AI can also support you whether you should go for bare metal architecture or you should go for RTOS architecture based on the complexity of your particular system. So you feed some data of your system and it can suggest whether you should do bare metal or RTOS. It can handle the task priorities. It can handle synchronization between the tasks. It can also be used for event-driven application or polling systems also. Protocols and review, as I said, Modbus can SPI, URI to C Ethernet, all protocols you can generate a code for that. It can handle CRC mechanism, frame validation, code review, and you can say the code optimization. So everything, these are the ways how AI can help us. The most important thing is what AI cannot do. So it cannot test hardware. Of course, the hardware testing is under humans forte because it has to be done manually. So it cannot directly test your hardware. It cannot guarantee real-time behavior. The most important thing is whenever you design a particular application using AI, whenever you generate a code using AI, you cannot rely completely on this because it cannot guarantee a real-time behavior. If you, for example, if you are developing a system for, let's say, car airbag opening. So, sorry, every modern car will have airbag, and the airbag should open in the case of collision. So you know that whenever the collision occurs, the airbag should open within some particular time window, and that time window is in terms of milliseconds, like 1 millisecond, 2 milliseconds, or 5 milliseconds. So you need certainty that within 5 milliseconds of the collision, your airbag must open. If it opens before that, it's too early, and that can malfunction. Like if there is no proper collision, if there is no higher impact, then also the airbag can open. And if the airbag opens like after 1 second, there is no meaning of that because within that time the accident will happen. So in that these kind of scenario where you require real timeliness, you require the response at a particular time, you should not completely rely on the AI generated code. At any point of time, you should not rely on the AI generated code because today I will show the demo of the same thing that the AI code cannot be directly copy pasted. But still, if you are designing for very safety critical system, then of course you need to double check. So it cannot guarantee the safety critical operations. Now, as an engineer, how we shall use AI? So obviously the suggestions must be verified. Whatever AI is suggesting, you must verify those things because I have seen number of times, like I generally ask ChatGPT, like I'm using this particular IC or I'm using this particular CPU and I want to use the ADC and it suggests me the pin map. So why I'm doing this? Because if I select a particular CPU, the CPU can have like 144 pin package or 176 pin package. And out of this 144 or 176 pin, which pin can work as an ADC input, which pin can work as a timer output, which pin can work as a CAN communication. So I can do it, but I have to read I mean, like many pages of the data sets. So instead, I'm using the chat GPT for the same. I just enter the MCU part number and I ask the questions that I'm using this particular CPU or MCU. Suggest me the pins which can be used for ADC, suggest me the pins which can be used for the CAN communications, etc., etc., etc. So in that case, whenever it gives me a response like these are the pins or these are the modules like ADC1 or ADC2 or ADC3, something like that. I always verify, and I found number of times that there are bugs. So whenever we have suggestions from the AI, you should verify first. Do not blindly trust 100%. You verify. Verification doesn't take much time because you just need to go and check that pin only. I need not to find the whole pin map to find the ADC pin. But if AI has suggested one pin, I will check that pin whether it is correctly working for ADC, correctly working for timer or not. So that's what the thing is. You have to verify the suggestions. AI is a co-pilot for firmware engineers, not a firmware engineer itself. Most important thing. It is not an engineer. It is just a co-pilot. So it is used to support you. It is used for your help. It is not used for a complete designer. So firmware engineer, at least at this point of time, cannot be replaced by AI. Yes, of course, the firmware engineer can take a help, but it cannot be completely replaced. It can almost save a lot of hours. If I have to develop a code for a particular application, if I require 200 hours with the use of AI, maybe I can complete those particular development within say 50 hours or 60 hours. But those 60 hours are required. I cannot say 0 hours. Next, it accelerates the thinking and development and reduce time to market. The most important for any entrepreneur, for example, I have to develop a product for my client, then the most important thing every time, each and every client has this priority like time. every time they ask for as soon as possible. So I have to do it as soon as possible, and that's why I'm using AI. It accelerates your thinking, development time, and reduce your time to market. Engineering judgment remains essential. So you need to judge things based on your gut feeling, based on your engineering fundamentals. So that's why it's like you need to verify everything. One must logically analyze the generated code and debug on test bench before using for real systems. Most important, directly do not dump the code in the systems and just believe that system can work. It can result into catastrophic failure if it is the system like designed like that. So most important thing, you verify your code on a local if it is possible. If it is everything is working fine, then you can migrate those codes onto real systems. Okay, so now let's come to the point. Like we are now going to design a particular system today itself live. And the demo, what I'm going to give you today is a quadcopter flight controller firmware development. And basically, if you can read the task is generate a code for a quadcopter flight controller for attitude measurement. So I'm not going to design a full flight controller code for the drone or for the quadcopter. I am just designing a code, a part of a code like only attitude measurement. What is attitude? So you can read over here. Attitude refers to the aircraft's orientation in space relative to the Earth's horizon or a fixed reference plane. This is defined by three rotational angles, pitch, roll, and yaw. So more precisely, if I say like, just a minute, can you see the drone with me? Chirag sir, this is visible. Yeah, okay, thanks. So I have this drone, and now what I'm suggesting is this drone will have certain angles in the space with respect to Earth, and those angles measurements are to be done. So if I again go back to my screen, okay, let me share the entire screen. Okay, so here you can see a kind of a video, a small video. If I just scroll it slowly, you can imagine that there is an aircraft. So you can replace aircraft with any object like a drone, quadcopter, octocopter, etc. Now, this movement, this movement is the nose up and down movement. This is nose up, this is nose down, nose up and nose down. This movement is around this red axis, around the red axis up, like you can see. So this movement is called the pitch. It's the pitch, and the angle is called the pitch angle. For example, if the nose is like this, so from the flat surface, what is the angle of this nose? And that is called the pitch angle. So this movement is called the pitch movement. Similarly, this movement, you see, this movement is around this green axis. See, so this movement, I mean left and right tilting, is called the roll. This is roll movement. And very similar, this movement, just rotate around this blue axis. This is called the yaw. This is yaw movement. Clear? So in general, aircraft position is defined by three angles in a space. One is the pitch angle, then the roll angle, and a yaw angle. Why we need to understand this part at least? Because I'm designing a quadcopter flight controller firmware, and for that I just need attitude measurements. So I need the actual angle of the roll, yaw, and pitch. Now, okay. I have this drone. Why why I need to know this pitch angle, roll angle, and yaw angle. Why I need to know? Because whenever I design a flight controller system for this particular aircraft or this type of drone, the basic thing is the sole aim is to keep your brain steady. Now, how your drone can be steady? If all four motors are running at a constant speed or the same speed, there are no external forces of wind or any other object. So imagine there are no external forces. All four motors are running at the same speed and they all four are developing the same thrust, upper thrust. So your drone will remain steady. This is how your drone remains steady in the space. Now, if your drone is slightly inclined like this, and you know now this angle is a roll angle, so it's slightly rolled. If your drone is slightly rolled because of the wind from this side, now what will happen? You have to again control the orientation, because if drone is like this, it will move in the left way. Like, so assume this is a steady drone. Because of the wind, it tilts your drone like this, and because of that your actual forces are not upward, but the force is like inclined, because when the drone is steady, the force is upward. When the drone is inclined, your force is also inclined, and that's why the drone will now shift on the left hand side, so it will move its position. In that case, what you have to do, you have to again bring the drone to the level, right? And how you can do it? For that, you must know at what angle currently the drone is. For example, you have to continuously monitor the angle of pitch, roll, and yaw. So whenever the wind makes your drone tilts like this, your firmware understands that your current roll angle is not zero. The current roll angle is, let's say, 10 degree or 9 degree or 5 degree or 7 degree, whatever. And you again have to make it 0 degree. So then there will be correction. So for correction, at least you need actual measurement. And that's why you need to know this attitude of the drone. Correct? So what are the steps we are going to do today? So the steps is, first, you study the flight controller hardware for which the firmware is to be written. The most important thing is you must decide your hardware. For example, I have a drone, so I know which hardware is there. So you study the hardware. Then you must have the knowledge about the MCU and its tool chain for integration of the code and downloading. Then you must have the knowledge about the quadcopter working principle, control logic, etc. Fourth, command the AI tool with the clear instructions about the task with as much detail as possible. So once you have the knowledge about the systems, now you can start giving command to the AI with clear instructions with detailing. Then, most important, before generating a code, you just ask AI if it has any questions. So we explicitly write down in the prompt that these are my systems, these are my requirements. Do you understand it clearly? Do you have any questions? Whenever you do this, it will make sure that the AI understood your task correctly and you both are aligned on the same page. Then generate the code, check and understand the logical flow. Instruct AI for correction if something is not in the order. So the most important, whenever AI generates the code, you check, understand the logical flow. And then if you just find something is not proper, the AI instruct AI immediately and correction is required. Once the logical flow is correct, then you integrate the code to the MCU tool chain. So obviously you have to copy the code into some and paste it into some of the editor or some of the IDE what you are using for your own MCU. That step is required. Then you compile the code and try to fix compilation errors. There may be compilation errors. It's not possible to have zero compilation errors, but yeah, you try to fix compilation errors, and then in that process, you may need to correct the code again multiple times as you find some needed modifications. And after successful compilations, download and debug the code to verify. Now, if you find something which is not working correctly, like logical error, if not fully correct, then you may need to repeat the previous steps. So do you understand this particular thing? You can just write in a comment if you have any questions, or Are you aligned?
Yes, participant, you can write in the chat box. Chat box is open.
If you have any questions, then you can also ask. Okay. So now let's go for the real example. I will show you. Okay, so the first step, study the flight controller hardware for which firmware is to be written. So I'm just opening my hardware. So currently I'm using this particular board for my drone application. I just rotate it. Okay. So the name is Omnibus F4 V2 Pro. This board is called Omnibus F4 V2 Pro. This is the board ready designed, and it has this CPU. If you can read, the CPU is ARM STM32F405 RGT6. The precise number is this. Now this board has onboard IC for gyroscope and accelerometer. So you know what is gyroscope and accelerometer. Gyroscope and accelerometer are the two sensors which you may know. It also comes with your mobile phone. Sometimes some modern mobile phones have gyroscope and accelerometer. At least accelerometer is there. Gyroscope is optional, but accelerometer is there. Why gyroscope and accelerometers are there or part of your mobile phone? Because when you tilt your mobile phone, the firmware detects that your mobile phone is horizontal or vertical, and when it is horizontal, then your YouTube or whatever video you are watching, it just adjusts on a portrait and landscape, something like that. So the decision whether your phone is vertically held or horizontally held is taken by the accelerometer inside the firmware. But for the phone application, you need not to precisely find out the exact angle of the phone, because we don't want that phone is now moved to 1 degree or 2 degree or 3 degree. We just need a switch. Like if it is horizontal, it's okay. If it is more than 100 degrees, horizontal. If it is less than 30 degrees, it's vertical, something like that. So there we need not to have such a precise control. But for the drone applications, we require even the control of 1 degree, because 1 degree accuracy can result in a tilting. If you ignore 1 degree tilt, then your drone will not remain steady. It will continuously drift in air, left and right, forward and reverse, something like that. So now come back to the point. You require two sensors. One is gyroscope and one is accelerometer. I'm not going into much detail of those sensors, but just give you a brief. Gyroscope gives you the output in terms of degree per second. It's a rotational angle. It can give you rotational velocity, sorry, not angle, but rotational velocity. The degree per second. It will not give you directly an angle. If I show by the drone itself, when the drone is steady, my gyroscope output is steady, like zero, because my drone is not moving. So rotational rate is zero, right? When I start rotating my drone like this, there will be a rotational rate like some degree per second. This the speed of rotation is, let's say, 5 degree per second or 10 degree per second. Suppose my rotation stops here. Suppose if I keep my drone over here like this, then again at this point of time, the output of gyroscope will be zero, because now even though the angle is not zero, but the rotational rate is zero. So gyroscope output will become zero. So gyroscope, keep in mind, does not provide you the actual angle. Gyroscope only gives you the rate of rotation. Once your drone is steady, the rate of rotation is zero. Now the gyroscope is a 3-axis gyroscope. So it can detect the rotation in this direction, in this direction, and in this direction. So it's a 3-dimensional rotation. So it's 3-axis rotation, right? So this is how you can So what you have to do is, once you have a gyroscope reading in particular axis, you can you can integrate those values and you can find out the actual angle. For example, if my drone is moving in this direction with 100 degree per second, if this is 100 degree per second rate, and if I at every 100 millisecond, if I calculate my angle, so at after 100 millisecond, what will be the angle, actual angle at 100 degree per second is the rotation rate, and after 100 millisecond, if I measure the angle, it should be 0.1 into 100, so 10 degree. So I can assume that within 100 millisecond, my drone has moved 10 degree of rotation. So that way, indirectly, I am calculating the angle of my drone. This is roll angle. Similarly, I can find out the pitch angle and I can find out the yaw angle. So important point is not just worry about the theoretical part of gyroscope and accelerometer, even if you don't understand everything, because we are not actually dealing with the drone application right now. I'm just explaining these things because those things are required to prompt the AI. So the important thing is gyroscope alone can give you rotational rate, and you can find out the rotation of your drone or the angle of your drone. But gyroscope in practice alone is not sufficient. Why it is not sufficient? Because the gyroscope will always have a drift. So for example, if the drone is moved like this, your angle is 10 degree, and if the drone remains steady, then over the period of time, the gyroscope drifts, and your angle will keep on moving like 11, 11.5, 11.12. Your drone is steady, but what you measure in your firmware, that angle will be incorrect after some period of time. So gyroscope is not a steady thing. It's always drifts, and that's why it's an error generator. So you can rely on gyroscope for a short term, but you cannot rely on gyroscope for a long term. That's why gyroscope alone is not sufficient for angle calculation. That's why you require one more sensor, that is called accelerometer, right? Now, what accelerometer will measure? Accelerometer, as the name suggests, will always measure the acceleration on three axes. Again, the accelerometer it has three axis accelerometer. So x-axis, y-axis, and z-axis. So three axis accelerometer is there, and all the three axis acceleration it will measure. Now, if you compare about the z-axis, the vertical axis, there is always an acceleration. Why always an acceleration even if your drone is not moving? Because of the gravity. So your gravity is an acceleration of 9.81 meter per second square. So if your drone is steady, you always have to have some force on a vertical side, that some acceleration on the vertical side to counterbalance that part. And that's why if you measure a steady drone accelerometer output, x-axis accelerometer output will be 0, y-axis output will be 0, but the z-axis output will be 1 corresponding to 1 g, like per unit system, something like per unit system. So it's 9.81 meter per second square. Now, so then the question is, why accelerometer cannot be used directly? Why to use gyroscope? The problem is accelerometer is always a noisy. Accelerometer generates so much of noise. Now in this application, there are always a noise, because whenever you operate your drone and there are 4 motors or 6 motors, and these motors runs with so high speed, and these motors generate so much of vibration, and then all vibrations actually go inside the firmware, inside the your hardware, your board. So your board will vibrate with some frequency, and those vibration will actually results into accelerometer noise. So your accelerometer is noisy, and there are so many ways to reduce the noise. If you I think you cannot see with this hardware, but I have provided some damping. So my board is not directly connected to the frame with hard screw. There is a soft damping, so that can minimize some of your noise. But still, some of your vibration is minimized, but still accelerometer is a noisy thing. So it's a different thing. On long term basis, accelerometer is fine, but short term there is a noise. So for long term, you can average out the noise and you can have a clear angle calculation. Gyroscope is the opposite thing. Gyroscope is a short term good, not a long term good. So what we have to do, we cannot use only gyroscope or only accelerometer for angle calculation. We always use both, and something called sensor fusion. This is most important theory for any drone application. There is always a sensor fusion. So for a particular task, you may have 2, 3, 4, 5 sensors, and you go with the fusion of all the sensors, and somehow there is a control logic like Kalman filter, extended Kalman filter, or complementary filters. Those things, those control logics will give you some kind of the trade-off between the noise of accelerometer and the drift of gyroscope. And that way you can have precise angle measurement of your drone. So this is the only theory I just wanted to touch upon, because now with gyroscope and accelerometer, let's see the image again. This particular board has the gyroscope and accelerometer chip named MPU 6500. I'll show the datasheet of this same chip. This is MPU 6000 chip. There is also other version MPU 6050, but on our board we are having this particular chip MPU 6000. And if you read a datasheet, just an overview what this chip has, you can see this MPU 6000 is the 6-axis motion tracking device that combines this one, 3-axis gyroscope, 3-axis accelerometer. The most important thing, the single chip has both the sensor, 3-axis gyroscope and the 3-axis accelerometer. But now you can see these datasheet are having 52 pages. Like you can see, there are so many pages. And there are some registers which I have to read. There are logic of communication, how to communicate with this chip, like I2C bus operation is possible, then SPI bus operation is possible, how to connect, everything is there. So like this is using SPI interface, then you have internal clock generation, how you can read the sensor data, what is the amount of FIFO it has, what are the interrupt possibilities. So these IC has like 52 pages of data sheet. So if I want to write a code for myself, then I have to read almost 40 pages or 50 pages out of this, so that I can be able to know everything and then I can code. But because of the AI, what is the advantage? I'm not saying I don't need to read this page or any single page. I have to read, but at least I can read 10 page or 12 page or 15 page at the most. Within that thing, I can be able to generate a code using the AI. So that's the benefit. Now, this is the board. Sorry, the board is this, where the CPU is STM32F405. So as I told you, you have basic knowledge. You must have basic knowledge of this particular CPU. So I have downloaded the datasheet of the same CPU. So this is the datasheet. You can see STM32F405. Now, just important points which I already highlighted. It's a core ARM 32-bit Cortex M4 CPU. CPU runs at the most 168 megahertz of clock speed. 1 megabyte of flash memory is there. 192 plus 4 kilobyte of SRAM. All these things are there. But there are a lot of things. You can see that the data sheet spans 205 pages. So at this moment, you don't need to read 205 pages, but yes, you must require some knowledge, and you must require knowledge about how to integrate. So you know about the tool chain, how to download the program with inside the chip, where to write the program and how to debug. So those things are always a prerequisite, but that always the user dependent. So if I'm using this board, it's not compulsory that you always use this board. You may be using some other board and other controller, so those are known to you. Okay, now with this information, let's try to give a prompt to the AI to generate a code. Let's try to generate a code first, check first, then we will integrate those code to the IDE, I mean the editor and compiler and etc. And then we'll try to solve some issues, and then we'll finally see the working hardware. Okay, so the ChatGPT screen is now open. Okay, so first thing I'm writing is the just overview of the task. So see what I'm writing. I am designing a flight controller firmware for STM32 F405 MCU with MPU 6000 chip. Okay. Communication between MCU and MPU 6000 chip is via SPI, correct? So we are using SPI communication. So as you know, MPU 6000 chip communicates to the MCU by two. There are two way possible. One is I2C, one is SPI. But I2C is slower communication, so always I prefer SPI over the I2C. So at the moment I'm choosing SPI because already the board is connected with SPI connection. So this is how I instruct AI. The communication between MCU and MPU 6000 chip is via SPI. Okay. Now the most important point, your STM microcontroller connects to MPU 6000 chip, yeah, via SPI. But what are the pins? That is most important. Which pins are connected? So for that, of course, you require the hardware knowledge, and that's why I have downloaded the pin map for the same hardware. So the pin map says, as you might be knowing that SPI requires at least 3 lines or 4 lines. Now here, these are the 4 lines. First, second, third, and fourth. The first one is the chip select connected on MCU PA4, pin number PA4, SPI clock PA5, SPI master in slave out PA6, SPI master out slave in on PA7. What is required? I have to clearly tell the AI that these pins are there for the SPI communication. Otherwise, the AI does not know that I am communicating via which pin. So I am just typing a scenario like SPI pins are as below. Chip select PA4, then SCK PA5, then MISO PA6, and MOSI PA7. Correct? So these are my pin connection to the MCU. Okay, now what else is required? Let's think again. Before giving a command to the AI, let's think and let's provide as much detail as we can, right? So the thing is, the most important thing, if we are able to write the firmware correctly, suppose we are able to write the firmware correctly and the output is correct, the correct angles are read, how can we verify that the angles are correct? At this point of time, at least we need some verification because we are not designing complete flight controller hardware, flight controller control logic. We just want to design that your code should read the actual angle of your drone, but the drone angle should be readable by us, and that's why we require some kind of debugging. And how we can debug? The most important point is, let's say we already have a kind of a terminal software on the PC, like serial terminal software. So what I prefer is, like, what my MCU should provide all these angles to the terminal via serial communication, and I should be able to read those things on a terminal. So I'm just typing the same thing. I need to read, let's be specific, roll and pitch angles on terminal via UART communication. Okay. But now the point, which UART? One MCU can have, let's say, 5 UART, 6 UART, 2 UART, 3 UART. There are a lot of hardware, serial communications hardware, and many number of pins can work as a serial transmit or serial receive. So now the important point is, again, you have to check your hardware, that whether your hardware supports this or not. So if I go back and if I open my hardware block diagram, Here I can see there are a lot of things, TX3, RX3, TX6, RX6. If you read, if you see my cursor, there are some things. But the most important point, if I take the hardware on my hand, or if you can see over here, there is a USB port. You can see it's a USB 1 port. This is a micro USB port which can be directly connected to the terminal, and STM, because I know this thing. This is the knowledge which I already have. That's why I can able to do this. So this USB port can act as a virtual COM port. So STM has this facility, this particular MCU has this facility, that the USB connection can act as a virtual communication port, virtual serial port. And when you connect a cable from this to your PC, you can directly have a COM port just like you have connected a serial device. Once you have a COM port on your PC, you can send as many data as you required via that serial communication. So what I have to suggest, that I'm writing in the chat box. So I'm writing, I am going to connect USB connector to the PC. Here I'm also specifying I am using Omnibus F4 V2 Pro board. Okay. I use USB as virtual COM port. Okay. So what we have done, let's verify first. We have provided a task like I'm designing a flight controller firmware. Communication between these two chip is via SPI. So we have given the chip gyroscope accelerometer chip name. We have given the name for a microcontroller. We have provided the connections. Then we provided the details how we will read those angles. We read those angles, roll and pitch angles on the terminal via UART communication. And I am also specified that I am using Omnibus F4V2 Pro board. I'm going to connect USB connector to the PC, and I use USB as a virtual COM port. Okay, I think let's these details are fine at this first guess. And the most important, what I have to write. Let me write this. Do you understand this requirements? Do you have any question before writing the code? This is the most important, because sometimes it can ask you the questions which are very important, but you might have missed in the first case. So sometimes it asks you some questions, and that would change your perception, that would change something, or that can that could be very much important for you. So let's first try to check the response, what AIV is now responding to us. Okay, so now the response is yes, I understand what you want. MCU is STM32F405 with this board. IMU, this is most important. See, the IMU name is Inertial Measurement Unit. So it has identified that this chip is nothing but 3-axis gyroscope and 3-axis accelerometer, combinedly known as IMU, Inertial Measurement Unit. The pin mapping is there. Goal, read IMU data, compute roll and pitch, print them to a PC terminal via USB virtual COM port. Before I start writing code, here are the only things that materially affect the implementation. Okay, now tool chain, project base. Are you using this hall? Okay, USB CDC versus UART wording. Okay, so my mistake, it should be USB CDC, not UART. So something like that. Sorry, it should be UART, not USB CDC. MPU 6000 configuration. This, of course, yes. Update rate, very important. At what speed you want to update your, you want to read your data, and what you want to display your data. That is the update rate that you have to provide. Okay, so now let's give the answers. First one, or let me write like this. Here are my answers. First thing, tool chain. I'm just copying. This is fine. STM32 plus Hall. This is what my tool chain is. Okay. Then second point, UART with VCP. This is what I required. More specifically, UART 1. Then configuration. Do you want raw accelerometer based roll pitch? Simple works are not accelerating much, or basic complementary? Yes, the most important thing. See, it has provided me an option how you want to calculate your roll on pitch angle. Just raw accelerometer based angle, or using gyro plus accelerometer, as we just talked about, gyro plus accelerometer fusion. This is much better, stable. And for these, we have many options like basic Kalman complementary filter, Mahoney filter, Kalman filter, etc. etc. So here I am specifying this thing. I need complementary filter with gyro plus accelerometer. Okay, this is my third answer. The fourth one, update rate. Of course, this is very much important. Now here I provide the update rate. I want to read the angle at 1 hertz frequency. 1 hertz means sorry, not 1 hertz, sorry, 1 kilohertz frequency. 1 kilohertz means 1 millisecond. So every 1 millisecond, I will read the chip and I will find out the new angle. So that is what I currently required, 1 millisecond angle read. And also I specify and display on UART, or let's say not UART, on terminal. Okay, with 100 hertz, or let's say uh, mm, 2 hertz. That's fine. So what is the meaning of 2 hertz frequency? 2 hertz means every 0.5 second. So every 0.5 second, I will display on a terminal, because if it is so fast, then your eye will not be able to see each and every reading perfectly. So let's say how fast you can see on a display, or how fast you can see on a terminal. So I keep it with 2 hertz. So every 0.5 second, I will have a new reading. So that's why that's what I specified, 2 hertz. Okay. Now, fifth point. Okay, we don't have a fifth point, but let's think if we miss something or not. Okay, let's ask this, or any more question? Okay, one point I missed. I can just provide. I need bare metal core. I don't want to use OS, because at this moment the complexity is not so much. So I don't want to use the OS, and OS always adds the overhead. So I just need bare metal core. Okay, let's see the response of AI. Okay, no autos, output over USART1 to USB UART VCP adapter. IME loop at 1 kilohertz, terminal print 2 hertz, complementary filter, no more questions needed. Okay. Writing notes. Okay. Okay. So already it has created me 3 files: main.c, mpu6000.c, mpu6000.h. So now I have a code generated by AI. I have to bring those files, those codes to my IDE, and then I have to verify. Okay. So now let's do it. Let's bring those codes into IDE. So for that, let me open the IDE first. So I'm opening STM32 Cube IDE. This is my toolchain for developing the application based on STM32 microcontrollers. Okay. Now I create a new project here. So let's say I'm creating STM32 project, and then it will ask me for the MCU. Okay, here I'm writing STM32F405RG, exact number which I found on the chip. So this number is this one. So I select and then press next. I have to provide the name of the project. So I'm just writing I am using AI. Okay. Let's keep the default project location, no problem. Next, the firmware library I have is 1.28.0, and then just press finish. Okay, so now you can see the project is created with some structure. I just close this file, IOC file, and on the left hand side you can see it has two main folder. One is the inc folder inside the core, this one inc folder, that is include, and src is the source folder. These are for the user, and drivers and other folders are for the driver libraries. So currently I've opened the main.c. Now I go back to the chat gpt and see what it has suggested. Now here, this main.c I can directly copy. So this is copied. I completely replace my main.c, save. What else I required? Then I have two more files. See here, one is mpu6000.h. So this one, and the other is mpu6000.c. Okay, so what I do, I have to add those files. So I can right click on the inc folder and add one file, new. Then the header files, I'm adding one header files. I'm just giving a name mpu6000.h, finish, and I can straight away copy this file and paste it over here. So this is my header file. Then I can go to source folder, new, add a source file. I give a name mpu6000.c, finish. And then I go down. This ChatGPT has given me mpu6000.c file. So I copy and I just replace it here. Okay. So now I have integrated code main.c, mpu6000.h, mpu6000.c. Now I have to compile and be ready for the shock, because whenever I compile, it may not compile properly. It can give you some error. So I'm compiling, and you can see total 46 errors and 7 warnings. So now comes the part, like whenever you blindly copy pasted something, it is never going to work. So AI, as I said, AI is surely helpful for us, but that doesn't mean it can replace, at least at the moment, it cannot replace. So there are a lot of things which you have to fix. Most importantly, why these things are failing, that I have to check. So here, I'm just clicking on one of the error, like this error, and that error says unknown type name SPI handle type def. So something is not meaningful for the compiler. This thing is not known to the compiler. Now, if I have a prior experience, or if I have some reading, if I have worked with this CPU, I already know that these are the syntax used by the actual drivers of the CPU. So problem is, there are no driver installed. There are no driver libraries. If you just click on the driver folder section, there are some basic drivers are there, but here you cannot see any SPI driver like Cortex, DMA, EXTI, Flash. These are all required only for functioning of this the Cortex system or the core part, but not for the SPI driver. There is no UART driver, nothing else. So that's why these things are defined in a particular peripheral driver files, which are currently missing. So what I have to do is, and this thing has to be manual, I have to open the IOC file again. So I'm opening the IOC file again. Now I have to set at least few things over here so that it can work. So first thing, I have to set the clock speed. Okay, one important point. I have to ask ChatGPT, what clock speed you set for the CPU, right? What clock speed here it has set. Okay, I set the CPU to 84 megahertz. Now, I don't want this. It has used the clock source of HSI, that is internal RC. Then let me specify. Board has 8 megahertz crystal. I use PLL and clock speed should be 168 megahertz. Now it has corrected the things. Now it says that you have to replace your old system clock config function with this function. So I just copy the function, go to IDE, go to main.c, and in main.c system clock config this function. So I just copy this function and paste the new one. Okay. Okay. Now you go to again this IMU. You go to RCC because now I'm setting up the clock. So high speed crystal. If you don't understand this part, don't worry. This is just a demo how we required human intervention and how or what level of support AI can give. So you can just imagine that AI has given me some code, but there are few things, few tricks which I always need to do. So for example, here I'm checking the crystal resonator setup, high speed crystal is available. I go inside the clock configuration. My clock speed, crystal speed is 8 megahertz, and I am running with PLL, and I require the clock speed of 168 megahertz. And that way I'm setting up my clock configurations. Okay, after this, I go back and I go to connectivity. I select SPI1 because I'm using SPI1 for this particular communication. I select the mode as a full duplex master because my chip is the master and MPU 6000 is a slave. Always these things are slave. Your controller is always a master, and you need both way communication. You have to read something, you have to write something, and that's why I choose full duplex. And inside this thing, I'm just keeping as it is because once we have the library installed, this setup is already done by the AI. So I'm not changing anything over here. Only thing I do is just check if everything is working. Parameters set. Okay, okay, okay. Everything is working. Everything is set up. And I go to UART1, USART1. Again, this USART1 I required for serial communication. So I select mode, asynchronous, and these settings are fine at the moment. And then I need the USB OTG because I'm actually connecting UART via USB. So USB OTG full speed, and I like device. I'm choosing my device mode as a USB. I don't want interrupt at this moment, and then I go to middleware. FS. Sorry, one of this USB device. Virtual comport. See, now I have this option of communication device class, that is virtual comport. So I choose this comport, virtual comport, and in FATFS, I don't need to select anything. Okay. Okay. Now I just press this and it will regenerate the code. So now the thing is, the code will be now generated by this cube ID. Okay, so this is a new code which I got. So now comes the integration part. Again, I have to go back to the ChatGPT and check the things which are missing. I go back to the main.c code. Okay. Okay. So if I start from the beginning, there are some include header file. So I must use this header file. Let's see what we have currently. We have only main.c USB device.h. So now I have to have all these things. So I just copy and add here. Now I go down, like I have a configuration of this thing. So I need all this thing up to main, copy and just paste it here. Then inside the main, I compare all init, system clock config, GPIO init, SPI1 init. That's fine because I stick with, see, the names are not correct. These things will not work. So I have to stick with the cube ID generated code. Then USART UART init, or maybe it has defined the more functions. So I will replace this part. System GPIO init, USART1 init, hall delay. Okay. Up to this part, this point. Okay. Loop, this while loop I have to copy. Copy the while loop. And I just paste inside this. Now, one thing I already see, there is no function inside the main for the USB part, for the USB device part. So then I have to instruct to change it. I can't see USB VCP part in main.c. I connect DFU USB port of Omnibus F4 V2 board to PC. See, it has only given the option of USAT1, not over the DFU USB port. So these are the ways you cannot directly copy paste. You cannot directly trust that AI has generated the very precise code, but you should know what is wrong, what is right, and then you have to correct it. Only thing is, I need not to type this much of code. Like it has given me a very good, at least very good structure. Only thing is the some missing point I can correct it. So now it has identified that USB native port is this, virtual COM port. Okay, okay, okay. Critical. And then, yes, then this you have to include USB device, USB CDC if.h. And then you had to add this USB device init function in the main. And you have to print, you have to call this function for printf of particular thing. You are transmit with this. So then you have to change everything and integrate in your main. So let's do it. Sorry, I'm just speaking continuously. Are you? I just want to check whether I'm still audible.
Yes, you are audible.
Okay, okay, sure. Thank you. So let me integrate all the change one by one and then let's see what we get.
Sir, are you presenting, sir?
Sorry. I think it's I am not able to do it. Is it visible now?
Yes.
Okay. Okay, so I just complete integration of this code, and now if I compile, okay, there are some errors, and if I just go through errors, it says timer handle type def implicit declares. Okay, okay, so now I understood what is wrong. We have initialized all the things, but the main point is to uh, to have this 1 kilohertz loop as we instructed to generate update rate of 1 kilohertz, like where it is. Yeah, here I have specified that I want to read the angle at 1 kilohertz. So for this 1 kilohertz time delay, I think it has used this timer 4, and that's why we have not initialized timer 4, and the timer 4 library file is missing. If you see inside the driver's block source, there is no timer library. Yes, no tim.c something, and that's why that's the problem. So timers is not initialized, and that's why this thing is giving me an error. So the solution is either I go back to the IOC file and I initialize the timer from there. But the problem is if I initialize the timer from there, then the cube ID will again change this code. And I don't want to change this whole code because I already integrated the changes from the ChatGPT side. So now what I just need to add the timer library over here. So for that, I will just look for the driver from somewhere else. Let's say, uh, let's say ADC 332. Let me check if this is STM32F4. Just thanks. Okay, so go back to the folder. 4 first include, and sorry, not here, drivers. Then let's click on any of the files, show to in Explorer, System Explorer. I will just copy the file from this. So here I look for the timer file. CC. Okay,
I
this should
think
be here.
I think your screen is not visible, I think.
Oh, still not visible?
No, it is visible, sir. It is visible.
Visible? Visible?
Yes. Yes.
Okay.
Shall I share again?
No, no, it is visible.
Okay, okay. Yeah, okay. So, okay, so what I'm doing is I have one more project where already this timer file is generated, and I just want to copy the same file here so that I need not to go to the cube window and uh, regenerate the whole code. So this is my folder, uh, driver folder, hall driver. I don't see any timer file here. So I copy this file, and I can just drag inside INC folder, and I can see now I have this 3 file. Okay, so now I have this file for timer. Similarly, I have to copy the source also. So for that, I go to the project which has already a timer initialized, and go to source. These 2 files are dedicated to the timer, and then I just copy this to the source folder. And is it? No. Okay. Yeah, now we have 2 files. Now let's build again. Let's see if it is still some error because there is some dependency. Timer handled. All time.h. It is there. Let's clean. Then build again. Okay, then I think something is required. I mean, I have to regenerate the code with the timer. It just take a moment. Okay, what I do is I don't want to lose this thing. So I don't want to lose this. What I do, I copy this first main.c somewhere. Okay, copy, and let's keep it in Notepad plus plus. And okay, and I also copy the interrupt file in other one. Okay, and then I can go for timer 4, internal clock. Yeah, I just update timer, so nothing else is required. That's it. As interrupt is required, I think. So then save. Yeah, generate the code. Okay. Okay, now I bring back this main.c. Okay, and interrupt file. Now let's check. CDC ready. Okay, so okay. Now I have to ask what is CDC ready. So uh, I will ask to chat because what he has done, it has actually generated the files with some function which are not in the standard OTG library. It has generated its own function. So I have to ask what is CDC ready. Okay. Okay, so it's all related to your okay. Okay, so you have to add this thing because it has not given the definition. CDC control FS, how you use in main.c. Okay, everything is there. Let's try to integrate this thing. Oh, sorry. Okay, can you see now?
Yes, yes,
Okay, so I have
it's
added this
visible.
CDC definition. Okay, now we can see we have no error, no warning. So finally, we come to the point where everything looks in order. I just check the flow in main, initialize all init, GPIO init, SPI init, USART, timer 4 init, USB init, then some printing, some basic message. Okay, here I have MPU 6000 in it. If it is not okay, then just print fade. But if it is okay, then go ahead. Calibration, it just do the calibration. Okay, good. Calibration is like taking a lot of samples. Sorry, I lost my mic. Okay. Can you hear?
Yes, yes.
Okay, okay, okay. So calibration, we are talking about calibration is just taking uh, some readings before you actually start your system, and so that for during that period you have to keep your drone steady so that actually it's a zero angle, and whatever the value gyroscope or accelerometer tells at that point of time, you consider that as an offset, and from every reading you have to subtract the offset so that you can have a perfect zero reading. So this is why these calibrates. Then timer starts. Okay, so it's a loop timer. It starts, and in the loop, it always checks for like the time is okay. Time happens or not after 1 millisecond. It reads MPU data, looks fine. AX, AY, AZ, GX, GY. Then it calculates the roll, pitch from the gyro, from the accelerometer. This is what the fusion is like alpha. It's a complementary filter, so it's a fusion, and then it just wait for the printing time. If the printing time is done, like 500 millisecond is completed, just print roll and pitch values on the terminal, and then uh, okay. If it is this is optional, but we don't want this, so we can just remove it. Okay, so I think this looks okay. What we can do is now we connect the actual drone with this, and let's see if we get the correct value. Just give me a second. Okay, so let me go to the screen. You can also see my screen as well as my video, right?
Yes.
Okay, so now I move my camera. Can you see the drone connection?
Yeah.
So this is now connected via uh, this connection, this blue thing to the PC. So now it's connected. What I have to do is let's go back to the PC, and I can open the terminal software. The base thing, first thing I have to uh, open the Arduino IDE. Why I'm opening Arduino IDE? I have nothing to do with Arduino, but Arduino has given us a simple terminal monitor software. So that's why I'm using Arduino. I don't want this anything. Okay. Okay. Here you can see the serial monitor. Now at this moment, serial monitor, you don't know the COM port. I think here you can see the COM port. These COM ports are not for the device, because device we have not yet downloaded. This USB to UART COM port will only appear once your the device is loaded with the correct software. So what I'm now doing is I'm downloading this program to the hardware. So this is downloading starts. Okay, waiting for debugger. Some issue is there because of this connection, but let me correct it quickly. I'll try one more time. Okay. Now it's downloaded. Yes, and I can just run. So now program is running and I can see there should be a COM port. I check on the device manager. Device manager. Okay, not yet. Just a minute. I have to download again. Okay, then I have to power cycle. Okay, one more thing. We have not connected the serial cable or the USB cable. So I have to join, otherwise the data will not come. So this cable is okay. Now it is plugged. Okay. Now you can see, can you see the data is coming?
Yes, yes.
So every 0.5 second, I get this reading. It's currently 0.12, 0.13. It's okay. Now I am, if you see my camera, just have to make a dual screen of myself. Let's see like this. This one. Okay. So what I'm doing is now I'm making nose up. So nose up means your pitch should be positive. So I'm making a nose up. Now you can see, sorry, pitch should be negative. That's correct. Sorry, it should be positive. So currently the pitch is on a reverse side. You can see it's a minus 32, minus 45. If I again put it down back, 0. Now I make a nose down. So opposite and plus. So I'm making opposite and up. So now the pitch is positive. And then I again put it down. So pitch is 0. Now I check the roll angle. So I move the roll angle. So left side, I am moving left side up. Yes, the roll is positive. That is correct. The left side up means roll positive. Put it down, 0. Then right side up, roll negative. That is also correct. And put it down, something like this. The only thing is currently the pitch. When my nose is up, the pitch is negative. When the nose is down, the pitch is positive. But that can be just corrected with a single sign. So that's not an issue. That's actually a sign matters for what, like for our system, we consider nose up as a positive pitch and nose down as a negative pitch. So value is important. The sign can be easily changed. So this is how AI helps us to generate the code. As you have seen this demo very quickly, I think within an hour or so, we completed this part and we were able to run the drone flight controller with actual data of roll and pitch angle. This is just a beginning part. After this, you have a lot of things to do for a complete flight controller, like design a control system, motor control, and everything is there. But one module is covered. One module we could finish within very short time. So that's the advantage what AI is giving to us. But you might have already seen that even I have to provide a lot of efforts. So it's not like every time AI will give you a perfect program. There are a lot of changes, lot of things, lot of corrections you have to tell them, and then it will again give us with the corrected code. So this is how the system currently works. Still, it saves a lot of time for me, like lot of typing efforts, lot of logical efforts, lot of reading efforts, and I can deliver the products faster. So I hope you have liked this particular sessions. And if you have any question, you can raise. You can connect with me any point of time. I would be ready to help for any other your embedded solutions, hardware, software related things or that. So that's it from my side. Over to you, Chirag sir. Thank you so much.
Yes, thank you very much. It was a uh, completely different approach, and I believe that it is very insightful that the people can use AI diligently, and it
Yes,
will be like AI driven rather than or AI assisted rather than AI driven, right?
exactly, exactly, exactly,
We don't want to lose our own acumen for just
exactly,
because AI
exactly.
is available, right?
No, no. At the moment, currently, AI is very good. Even this is I'm doing with the Chat GPT. But what I have realized, what I have experienced, Claude is way better in writing the code as compared to Chat GPT.
Yeah,
Claude is way better, but it's a little bit costly. So it's still I'm planning to move to Claude. But say yeah,
Claudia.
for coding at least Claude is very much better as compared to Chat GPT.
Specifically to
But
embedded coding, people use Cloud more
exactly,
than
Claude
ChatGPT.
more than that.
Mhm.
Exactly,
Yes,
exactly.
yes.
Correct. But at this
Uh,
point, at least I am at least it's a good thing that it cannot replace completely the human. Maybe next 5 years or 2 years, no nobody knows. It can give you a code which never needs any tuning.
right.
But still, I mean, it's so for still for safety critical application, military application, space applications, you even after 5 years or 10 years, you can never rely completely on AI. So those
Exactly.
things must be human intervented, not directly the robot thing.
Absolutely.
Yeah.
Any question, participants? Please write in the chat box if you have any.
I write my
Email.
company email also. This is my company, Embed Logics. I have a website, embedlogics.com, and my email ID, my personal email ID I'm giving, baby26 gmail.com. Thank you so much for your nice comments. Yeah,
Okay, so we thank Mr. Milind Trivedi for this very insightful session, and we'll look forward to some more in the future, maybe. Thank you, sir.
thank you so
Thank
much.
you. Thank you.
Thank you so much.
Thank you very much, sir.
Thank you. Okay, bye.
Okay, bye, sir.